Okay. Hopefully you can hear me. Excellent. Good morning, everyone, and welcome to MAE 106, Discrete Mathematics with Probability. This is lecture 27. Okay, and let's see. Hopefully the stream is coming through okay. Let me just adjust the bit rate. Okay. And today is the 17th. Okay, good. So what we're doing is Bayes' theorem, and it's kind of important theorem. Some people have considered it one of the most important theorems in modern day, just because so much of machine learning is based off of it. Traditionally, it's been thought that Bayes' theorem was first, let's say, enunciated in between around 1700 to about 1760, and this was, yes, the emails are still they are still being emailed out. Yes, I'm still working through those. Some people are getting them, some people haven't got them, and I don't know, sometimes my email is bouncing stuff back, so I have to check. So again, it was named after an English minister. His name was Thomas Bayes. He was born around 1702 and died 1761. And the date that they commonly give it is 1763 is when it was published. He was published a couple years after he was dead. Now, there's a couple things we could there's kind of two things that we can do. We can kind of look at the probability that so we're used to seeing things like we have a cause implies effect. We go the probability that the cause given the effect was seen. So this is kind of the idea that we had like the cause, which was we had like poison ivy, and over here we had a rash, right? Poison ivy causes a rash, but for instance, this is the probability that cause given the effect was shown. What's the probability that it was poison ivy given that there's a rash? So it's kind of the opposite way. And again, just because you have a rash doesn't mean that you necessarily got poison ivy. There could be other things that caused it. The other one is about updating probabilities in light of new information. gained. So those are kind of the two approaches. So we can use with Bayes' theorem. So as an example, in the textbook, and a couple other examples, was about when we had the World Trade Center attacks, that there was a probability that we had that it was an accident when the first plane hit. Then there was a second and then we updated basically our probability that this was an accident. So we had a certain probability that it was an accident, the second plane hit, and then we basically thought like our probability is almost zero that this was an accident. And Bayes' theorem can actually show this. Okay. So what is this Bayes' theorem that I'm speaking of? It all starts out with conditional probability. So we're used to writing something like okay, so this would be like E. So this is the probability of event F given the event E occurred. So what I'm going to do is I'm going to switch it. So I'm going to do not F, but I'm going to do E. So this is the probability that of E given F. So it's the probability that both occur over the probability that F occurred. Now we can also rewrite E and F . We had done that previously with the conditional theory. With conditional, you can rearrange it so you can actually have the probability of E times the probability of F given E. So let's write that in. Now, the next thing I can do is this F . So if I think about this, I can actually break this up into two parts. So this intersection right here, that I can write as E intersect F. And if I want to have all of F, the other thing that I need to think about is this one over here. And what that is that's everything outside of E that intersects with F. So that means, if I rewrite this over here, now, the other thing too is that these are mutually exclusive. So that means if I took the union of those, that is just equal to the individual probabilities. Where did the tip go? There we go. Okay. So that just means over here, what I've done is I've decomposed the F into E and F plus the probability of E prime and F and using this rule again over here one more time, I get the probability of E times the probability of F given E plus the probability of E prime, the probability of F given E prime. Okay. And this is what we call Bayes' theorem. Now, we could remember this, but oftentimes what I find is it's much easier to just use a tree diagram to kind of come up with Bayes' theorems. So, how can we do this? So, we're going to say that we have, okay, so instead of having to remember all this algebraic manipulation, we can actually think about it probabilistically. And probabilistically, I mean, we're thinking about it in terms of diagrams and just chains of events. So let's say that I'm going to say E and F are events. Let's say that E is the cause. Here is the effect. So because of that, I'm going to say that there's going to be a cause. I'm going to use the cause as the first thing. So there's two outcomes for this. You can have either the cause being there or not being there. And over here, you can have the effect being there or not being there. Same thing. Okay. So what I'll do is I'll start labeling this probability tree. So what you would do is you would start labeling kind of the numbers on here. So along here, this would be the probability of E. Okay, and then this would be the complement. Over here, now this is given that E has occurred, what's the probability that you have F? So I can write that as the probability of F given E. Now when you multiply these together, the probability of E times the probability of F given E, what that gives you is the probability of E and F happening. And we had done that previously. We had done this with the network, the hacker in a network, when we're talking about conditional probability, I think 2 lectures ago. Okay, so over here, this would be the probability that you have F prime or F complement given E. So again, you would just multiply the probabilities along the branches. So it's the probability of E times the probability of F complement given E has occurred. So that would be the probability of E and F complement. And then this branch, this would be E prime has occurred. And then on this branch, you have F has occurred then. So you have the probability that F given E prime. And similarly down here, you would have F prime given E prime. So again, I just read down the branches. So that would be the probability that E complement and F happened. Down here, it's the probability that E prime times the probability of F prime given E prime. And so that's E prime and F prime. Okay, so you're still probably wondering, okay, how do I come up with this formula then? And I go, yes, I understand. You want answers. Okay. So the way that we would come up with this is we have the probability of, let's say I want the probability of E given F. Okay. Well, we know that this has to be, just from our conditional probability, that this has to be E and F all over the probability of F. I'll pick this pen. So there's the probability of E and F. So here we go. So that's that branch. So you would multiply E times the probability of F given E. Okay. And now you need to find the branches where F has occurred. So in this case, I have right here, this is 1. So this is where F has occurred. And I also have this one where F has occurred. So I'll use a different color. Let's say that this branch here is 2. Well, then the probability of F is then this branch plus this second branch here that we're okay. And so that means if I write this out, the probability of E given F, which is this branch, so it's the probability of E times the probability of F given E all over. So it's the same one. There's branch 1 again. So the probability of E times the probability of F given E plus this second branch here, probability of E prime times the probability of F given E prime. And look, there we go. We have matched this formula. Probability of E given times the probability of F given E all over the probability of E times the probability of F given E plus the probability of E complement times the probability of F given E complement. And you can do this for all of them. You can do the probability of E prime given F. So that would be the probability of E prime and F all over the probability of F. So in this case, you have the probability of E prime given F. So that would be number 2 over here divided by, and you still have the probability of F. F occurs here, so along this branch and this branch. So this would be the probability of 1 plus 2. If I go further, I can use I can do the other 2 cases. So again, I have the probability of E and F prime all over F. And over here, I have E prime and F prime all over F prime. Now what I need to do is I'll just label whoops, I need to get rid of 2 other colors. So over here, what I'll do is I'll call this 3. Over here, I'll call this 4. So now for this one, what I need is I need branch 3. So I'll have branch 3. So again, this is where I have f prime. So I have f prime here, and I have f prime there. So this would be with branches 3 over 3 plus 4. And lastly, I could do it with e prime and f prime. So that's branch 4 over branch 3 plus branch 4. Okay. So let's do an example with this. So we talked a lot about medical testing, especially because of COVID. But there's also lots of other medical testing. So this one I use is like HIV testing, human immunodeficiency virus, and it's another epidemic or pandemic that's been raging for more than 30 years now. And we can actually come up with I believe there's some now home testing kits that they can do. So let's say that there's a home testing kit. Well, first of all, we need to know how many let's say that in Canada, the probability that somebody is HIV positive is approximately, let's say, 0.002. Okay, we'll say that there is a home testing kit. And we'll say that the probability that the test gives a positive, given that there is an HIV virus present, we'll say is 95%. And we'll also say that the test also has is also positive, even though the person is negative, and we'll say is 15%. Okay. So what we can actually do is there's some questions we could ask. Like, for instance, like the question would be, person tested positive. What is the probability that is HIV positive? This is also called a true positive. The second one is if a person tested positive, what is the probability that they're negative? And this is what we call a false negative. Okay, so I have this information. So what I'll do is I'll start doing a tree. So the idea is that we have a disease, and the disease then has some sort of effect. So in this case, we have the cause, and over here is the effect. Oh, should be, yes, thank you. It's a false positive. Thank you. Yes, thank you. Okay, so what I can do, so what we see then is you have the disease, and then you have the test. So you can think of that as this was our event E, and then we have F. So same idea. What I'll do is I'll construct a probability tree. So over here, so you can either have the disease or not. And over here, you can have the test be positive, you can have the test be negative, positive, and you can also have be negative. So what we can start to do is we can use our information that we have. So over here, the probability that it's positive is 0.02 or 0.002. Okay. Which then means that over here we have, we take the complement, which is 1 minus that. So you get 0.998. Okay. So we're also told then, so this is given that there's a positive for the disease, and you have a positive test. So this is the probability of, given that you have the disease and that the test is positive, this is where we would put a probability. So this is 0.95 here, which then also means that the probability of having the disease but testing negative is 0.05. Over here, this is where you have that you don't have the disease, you don't have it, it's negative, but you still test positive, is 0.15, which means that you don't have the disease and you test negative would be 0.85. Hopefully I did the math correctly. Okay. Which means that I'll use my 4 colors. Orange, yellow, there we go. So over here, this would be the probability of HIV positive and test positive. So we would multiply along the branches. So that's 0.002 times 0.95, which gives us 0.0019. I'll double check with the calculator. Let's pick 2. Or maybe I'll keep it consistent with the others up top on the previous page. So we'll do this one. So this is the probability that you have HIV negative and you got a positive test. So you multiply along here, which is 0.998 times 0.15. So that works out to 0.1497. Over here, probability positive and negative test. So that's 0.002 times 0.05. So that's 0.0001. And lastly, we have 4. So you have the probability that's negative and the test is negative. So again, multiplying 998 times the 0.85 right here gives you 0.8483. So I don't need any more of that information. What I can do is just looking at the question now, which is a person tested positive. So I can read this. So for part A, so if a person tested positive, what is the probability that it's HIV? So it's the probability of HIV positive given that the test was positive. So it's the probability of both of these occurring over the probability of the test being positive. So I look over here. So it's HIV positive and the test is positive. So that is branch 1 plus, oh, and I don't need any more plus because that's the only case that I care about, over. Now, there's 2 branches where it's positive for the test, so it's branch 1 and branch 2. So that works out to branch 1, which is 0.0019, all over 0.0019 plus branch 2, which is 0.1497, And I'll pull out the calculator for this. So I have 0.019 over 0.0019 plus 1.97. Add those together. We'll divide this. So this works out to the probability. That's our probability. So that works out to approximately 1.3%. Okay. And we have one more question, which was, if a person tested positive, what's the probability that it was HIV negative? So again, let's put that over here. So I can write this out. If a person tested positive, so given that they tested positive, whether that they are HIV negative. So we want where it's HIV negative and a positive test. Yes, this is not a very good home test. So exactly. This is why sometimes coming up with medical tests at home, the accuracy of the test has to be as accurate as the prevalence of the disease. So because it's a very low rate, means that the accuracy of the test has to go up really high for it to be accurate. Okay. What's the other thing that okay, so for this one, we have, there's the negative, so, and the positive. So this one would be, we would want branch 2. Go right over here. So I want branch 2 over, I would need branch 2 plus, I also need the case where this is positive, so branch 1 So what I've done here, instead of using the 0.0019, I need the 0.1497. Okay, that should be the same denominator from last time. So I get 0.1497 or 0.1497 over 1.1516. So not a very good. This would mean that it has a very high false positive rate. So again, this is, some people have called this the medical testing paradox, because while some people may say, like, okay, given that you have the disease, the test is positive, it comes out 95% of the time. Well, if I kind of change this order, instead, I'm looking at, not given that you have the disease, what the test is going to turn out, but given that the test is positive, what is the probability that you have the disease? You know, this is quite high, but surprisingly, this is quite low. Yes, it does sound very strange. And again, the reason for this is that because this number is so low, because the prevalence of the disease is so low, you have to increase this probability up much higher. So you can't have just 95% anymore. It needs to be closer to 99%. Okay. What do we have? Oh, and we're almost out of time. But yes. So again, when people are designing tests for at home, sometimes they have different principles in mind that they're trying to do. Sometimes they want something that's quick for rapid testing. Maybe they want to rule people out for having a disease, or they want to rule people in having a disease. But there's some trade-offs that happen. And so this is good for things like that are screening. If they do raise a flag, then they go to a gold standard. Okay, that's all the time that we have for today. For next lecture, we'll do some more examples. Bayes theorem. Okay. Enjoy the rest of the day, and if you have any questions, feel free to send me an email. Take care, everyone.